Okay, this works also. Well, thank you, Maria. I feel very honored to be delivering this special history talk. It's also a bit intimidating for me because the history of physics community is maybe half of the size of the QISS community. So usually I'm speaking to a much smaller audience. So I'm very flattered to be here. And yes, I also wanted to express my appreciation for the QISS consortium to having supported history of physics throughout the years, in particular via the History of Physics visiting program that Maria just alluded to, which was mainly administered by Flavio. I'm not sure if he's here. Oh yeah, there, very good. This is, has been greatly appreciated, and I think many fruitful interactions have come about through this, so well, thank you for this. To my talk, I'm giving a talk on the interpretation debate in quantum gravity, which is a historical overview over positions historical actors had in the early history of quantum gravity with respect to the interpretation debate. This talk is based on a chapter in this book, the Oxford Handbook of the History of Quantum Interpretation, edited by Oliver Frere. Perhaps this is actually interesting to some of you. Flavio has also a nice chapter in there, and mine is joint work with Alex Bloom, who was my PI at the time when we wrote this together. And the division of labor basically was that I focused on Léon Rosenfeld, who was the first person to attempt a quantization of the gravitational field by means of quantum field theoretical methods that were developed at that time, and then tracing his opinion on this endeavor throughout his career. And Alex's part was focused on the period between the 50s and the 80s, which this period incorporates the so-called Renaissance of GR, which saw a surge of work in the field of GR, with new mathematical methods being applied to GR to understand it better. And with this interest in GR came also a surge of interest in quantum gravity. And we basically cut the chapter in 1980 because afterwards, so the 1980s was the decade where both the quantum gravity community and the quantum foundations community were established as a community, in fact, in such a way that they became some sort of mainstream with, in particular, much more fruitful and more diverse interaction of positions. So it was a natural year to stop there, and it's up for future historical work, in fact, to continue after 1980. So in my talk, as I go through the slides, I will build up a diagrammatic scheme on how the respective positions on the quantum interpretation and stances on quantum gravity kind of saw an interdependence. It is important to understand, though, that this is not a logical diagram from like a logical how you can logically derive positions from another position, but it's a diagrammatic scheme that sketches opinions or statements of historical actors. So, and I have to drink a lot because I'm a bit sick, so that's the downside of it. Okay, and the first case I want to discuss is actually Léon Rosenfeld, who was a strong proponent of the Copenhagen interpretation, basically Bohr's speaks person at some point. However, before being that, he, as I said previously, was the first person to attempt a canonical quantization of the gravitational field. This is Léon Rosenfeld, but some years after he did that work, and this is the first page of the paper, which is called Zur Quantelung der Wellenfelder, which appeared in 1930. So the first attempt to do this appeared in 1930. However, shortly after, he became very critical of this whole endeavor, and I brought a quote to say this with his own words. So he said, "The first successes of the theory of quantization of the radiation field made it possible to suppose for a moment that within the framework of quantum mechanics, this method provided a rigorous mathematical expression of the correspondence principle. But in reality, further approximation leads immediately to meaningless results, so that the new formalism can only be conceived as a symbolic computational procedure." And he continues to say, "There's no reason to think that this same method is likely to provide us with an adequate description of the interactions between material particles, or to express the same idea in other terms, that the concept of the photon, which immediately results from the quantization of the electromagnetic field, can be legitimately applied to the analysis of fields other than pure radiation fields." So it's very apparent that he deplored the lack of physical grounding of the field quantization scheme and saw it as a mere formal act if you apply it to fields other than the electromagnetic field. And basically he would keep this attitude for the rest of his life. And the question, of course, comes up, why does he change his mind so quickly? And the reason I see is that the year after he came forward with the quantization of the gravitational field, he started to work with Niels Bohr on a problem related to the consistency or inconsistency that was to be found out of the measurement of field components of the electromagnetic field. And so my opinion is that through these intense work hours with Bohr, he gained a better understanding of, well, Bohr's interpretation of QM, and a better empirical sense for better empirical grounding of the equivalence principle, and this made him doubt the, well, physical grounding of this, of applying the quantization scheme to other fields than the electromagnetic field. So later in his career, he added to, so he voiced this opinion several times, though later in his career, he added another argument, which I think is also clearly derived from the Copenhagen interpretation, which is basically the necessity of the classical observer, where you specify the physical system under consideration on the one hand side, and an observer on the other side, which to Rosenfeld needs to be expressed in terms of classical concepts. And he argues in the following way: the metrical tensor appears as such a C-number specification of conditions of observation, and there is no logical imperfection in regarding as fundamental the classical unquantized form of the equations expressing the connection of metrical or gravitational field with the other field. So these are basically the two arguments that Rosenfeld came about with, that I think very strongly rested on his strong commitment to Bohr's interpretation of quantum mechanics. Though if you are committed to, let's say, the Copenhagen interpretation, you can arrive at the opinion that quantum gravity is necessary, and an example for this is John Wheeler. I'm sorry. So, John Wheeler, this is him. He arrived as at the opinion that quantum gravity is necessary by his program of daring conservatism, though he soon realized that another interpretation could be much better suited for his needs, which was the Everettian interpretation. Everett, who, by the way, as you might know, was a PhD student of Wheeler's in 56-57. And the reason he thought that Everett's interpretation is much better suited to his needs is that he arrived at the conclusion that he would want to quantize closed systems, such as the whole universe. And if you consider closed systems, there's no space for an outside, and in particular, no space for an outside observer, which is a core feature of the Copenhagen interpretation. So with Everett's interpretation, you didn't seem to need it, and this is how Wheeler argued for it. He said, Everett's concept of a universal wave function provided the only self-consistent system of ideas to explain what one shall mean by quantizing a closed system like the universe of general relativity. And Wheeler tried to sell this to Copenhagen, to Bohr and his group, and they discussed it in a seminar, but then completely dismissed it, saying that it's an insufficient concept in and of itself, and it seems to lack meaningful content. And and Wheeler tried to argue a bit against this, but eventually, and not so soon after, stopped citing Everett and trying to find a new meaning of the probability amplitude of a closed universe. And much later, then in the 70s, he did what, well, Alex called a uniquely Wheelerian twist, and I think it's quite apt, when he returned to the Copenhagen interpretation in this way. So he argues in his notebook, beyond the rules of quantum mechanics for calculating answers from a Hamiltonian stands the quantum principle. Quantum principle is an elevated name for basically Copenhagen interpretation here. And it tells what question it makes sense for the observer to ask. It promotes observer to participator. It joins participator with system in a wholeness, quite foreign to classical physics. We have to cross out that old word observer and replaces by the new word participator. So by this new interpretation of the Copenhagen interpretation, he made use of it for himself. Now, while Wheeler actually started to dismiss or not continue on the line of Everett's interpretation, there was actually someone else who did this, and this was Bryce DeWitt. Though he did not start with Everett as basically Wheeler did. This is Bryce DeWitt. But he did start with deriving the necessity of quantum gravity from an analysis based on an analysis of Rosenfeld and Bohr, where they argued for the consistency of the measurement of the electromagnetic field components, what I referred to earlier. And following the lines of reasoning there, he wanted to argue that actually it is necessary to find a quantum theory of gravity. And as you can imagine, Rosenfeld very heavily pushed back and said that this kind of argument is actually not viable. And it's unclear from the historical records that we found if this eventually made him to dismiss this line of reasoning. In any case, he did at some point, and then, as I said, followed along the lines of Wheeler and Everett and pretty much continued where they had left the matters, or Wheeler had left the matter. And he argued for this in the following way: to anyone educated in the Copenhagen school, such a function, like the universal wave function, is meaningless since it leaves no room for a classical realm. The external observer has no place to stand. In order to give meaning to a universal wave function, one must find a radically new way of looking at quantum mechanics. This is what Everett and Wheeler have done. And this is 1967, so 10 years after Everett's thesis and 10 years after Wheeler had started to think about this. So one has to say that while DeWitt also continued this and also continued thinking about quantizing closed, as you call it, closed finite worlds, this was not the only possibility for him as it was for Wheeler. DeWitt also considered infinite worlds where he deployed no interpretation whatsoever. Whereas he was very serious with Everett in the closed worlds, also employed this in like technical details, also when discussing solutions to the Wheeler-DeWitt equation that he came about with in this year in a series, in the first part of a series of 3 papers on quantum gravity. So I'm not entirely sure when I started, to be honest, but I feel I'm almost close to the end. So if you look at the diagrammatic scheme now, it seems quite manageable. The various positions they were up until then, like the 70s, and the amount of interpretations that were being employed or dismissed for these matters. And this actually only changed, as I said, in the 80s, where we saw a surge of and a great variety of interaction of considerations regarding the quantum foundations and quantum gravity. And one of the forecasts of the development to come was in a 1980s workshop at Oxford, organized by Penrose, Isham, and Dennis Sharma, where for the first time also other ideas were being discussed and other interpretations, if you will. The first being the de Broglie-Bohm interpretation by John Bell, where he basically argued, he gave the de Broglie-Bohm interpretation in Everettian reading, basically saying that's essentially the same interpretation, the only difference being that de Broglie-Bohm singles out as one branch as like as realistic, or as well, the real world, if you want, or as being real, and Everett, in the Everett interpretation, all branches are equally real. And then he argues that also in de Broglie-Bohm's interpretation, you have some sort of world function, world wave function, which could be equally employed as the universal wave function in Everett's interpretation, and thus one should try to make use of de Broglie-Bohm for quantum cosmology. So it seems that this proposal was received rather politely, and it's unclear to me if this was actually developed very seriously. This is also up for further, I guess, historical research. I just want to mention a final suggestion that was also brought up at this workshop by Roger Penrose, who basically proposed that the wave function collapse is brought about by a gravitational effect, and thus implying for, I guess, the first time that it's which interpretation to choose for this is not so basically quantum gravity is not the arbiter with respect to the several interpretations, but could actually be some sort of underlying physical principle of, I guess in this case, the Copenhagen interpretation. In any case, everything else that came after these, in this moment, vague proposals in 1980 is still up for historical research. The only thing I can say is that a lot of interesting things seem to have happened from this moment on, and I hope that someone will take it up. And with this, I will thank you for your attention.